Okay, section 2.2 is all about graphical displays of data. So in the last section, we looked at distributions, which are the statistician's main form of uh, displaying data. But if you are a data analyst or you're using data in any way, most regular people that don't work with data don't want to see it as a distribution. So we have a lot of different types of displays to make it more readable to the non-statistician or the non-data working person. So a lot of times if you're working in business, you would run a lot of data and then the data analyst would turn it into one of these types of graphs. So we have 5 categories. Some of these, like the first one here, are pie charts. Not a category, it's just pie charts. Some of them have different types of graphs. So in the bar graph category, we have bar graphs. We have what's called Pareto charts. And we have side-by-side bar graphs. In the next category, we have histograms. And relative frequency histograms. The fourth one is frequency polygons. And with frequency polygons, we have graphs called ogives. And then finally, we have stem and leaf plots. And with those, we also have dot plots and line graphs. So most of this is just going to be showing you what these different types of graphs look like, different graphs and charts, and talk about why we might want to use one over the other. A couple of them, like the pie charts, we're actually going to discuss how to create them. So for a pie chart, you divide your circle, because the pie chart's a circle, based on the relative frequencies of the classes. So you would take your frequency, divide it by n to get your relative frequency, and divide and times that by 360. And that would tell you how many degrees around the circle you would have to go. So let's create a little pie chart here. We made for housing, student housing. And this is an example that doesn't make a lot of sense right now in the current climate, but most of the time it makes sense. So we have 15 students living in a dorm, 5 in Greek housing, 20 in apartments, not in one apartment, and 9 that live in houses. So the first thing we need to do is get our sample size. So we add all the way down. 15 5 is 20, and 20 is 40, 49. This is our n. And so we look at our relative frequencies, 15 over 49 times 360. And you punch that into your calculator, you get 110. And this is degrees. 5 over 49 times 360 gives you 37 degrees. And 20 over 49 times 360 gives us 147 degrees. And then 9 over 49 times 360 gives us 66 degrees. Now I am rounding these. Again, you can use a quick little check to make sure you've rounded correctly. Add up your degrees, and they should add to 360. So 110 plus 147 plus 37 plus 66 should add up to 360. 7 and 7 is 14, and 6 is 20. Carry the 2, 2, 3, 6, 10, 16. Carry the 1, 360. Now, I rounded these. If you don't add up to 360, think about how you rounded. Did you round up or down? and see if you should go back to any of those specific numbers to round back up. When you're doing this, you always round to the nearest whole number, not a decimal. And then you just make a little circle. See how bad my circle looks here? Yeah, I've done worse. And you just approximate these values. So the first one here, dorms, has 110 degrees. So I'm going to start here, 110. If 90 is straight across like this, then 110 is going to be a little bit more. So I'm going to come down something like that. And we're going to label this D for dorm. The next one is 37 degrees. 37 degrees is not quite what's left here because we know to get all the way here should be 180. And right now we're at 110, so that's 70. So we should be about half of what's left here. So I'm going to do about there. This is for Greek housing. And then for apartments, 147 degrees is nearly 180 straight across, but a little less. So I'm going to do about this right here. So not quite straight across from this line. And this is our apartments. And then the final little wedge here, 66 degrees, is our houses. And then you would put the relative frequency, the percentage. So you already have the decimal, just divide it by 360. And it turns out this is 31%, this is 10%, this is 41%, and this is 18%. And you can make a little pie chart. And if you've ever made a pie chart in Excel, this is the calculation that Excel is doing in the background. So up next here, I've got bar graphs and Pareto charts. So we're not going to be building these because it would take forever. So this is the same data. This is the bar graph of our student housing. We have our dorms here with 15. We have our Greek housing with 5, apartments with 20, and houses with 9. That's a bar graph. It's just got the graph. It's got your labels, your axes, a title. A Pareto chart is just a bar graph that's ordered. Pareto charts are just ordered bar graphs. So instead of doing what came in order here, we ordered up greatest to least, or you could do least to greatest. We have apartments, dorms, houses, then Greek housing. And so that's all a Pareto chart is making the data look extra spiffy by ordering it least to greatest, or in this case, greatest to least. So up next, change the data. So now we're looking at class sizes for a couple math classes. This was last semester, I believe, is when I grabbed this data. So we have our frequency distribution, and now we have what's called the side-by-side bar graph. And this is really, you want to use this when you're comparing values for one category. So all of our categories are class sizes. And then each class that we have, both class in the statistical sense and math class, looks the same category. They're all seeing how many students are actually taking that course. So Math 104, Math 141, Math 96, and Math 119. And it's just a different representation. And you use this when you really want to know all, I don't know if you can read that on this recording, but all of these are labeled so you know how many people are in there. But it shows you in a more clear-cut sense who's in first, who's got the most and who's got the least, because you can see it lined up like this really nicely. So side-by-side bar graphs also have another use. That's when you're comparing iterative data. So we have the same data here, and then for fall 19 and then spring 20 of 2020. Okay, so this was 2 semesters ago. And this shows, again, it's the same category. It's class sizes, how many students were in the course. And it's the same classes, the same courses, but now we're just comparing it semester to semester. And so you can get that comparison really nicely here with the side-by-side bar graph. You can visually see the increase or decrease, if there was any increase or decrease. You always need a key to tell you which is which. So fall Fall 19 is the blue, and spring 2020 was the red. And so you can see most classes had a dip, except for Math 119. There's a lot more people taking that in the spring, and that, you know, makes sense since our class sizes last semester we dealt with all the craziness that we did. So the next type of graph is stacked bar graphs. Now, I don't think I wrote this in our thing, but this is another, it's a stacked bar graph. So this is another way to display the same data that we looked at in this example, iterative data. So you can look at fall 19 and spring 20 again, the number of people in those classes. And here, fall 19 is still in blue, spring 20 is still in red. And you see it's just a different representation of that data. So instead of putting it side by side like this, you stack it on top. This also gives you totals. So if you were also trying to see how many total things you were, how many total students were there, you could see that here because it would be labeled. And I know, again, the recording you can't see it, but you have the packets. The numbers are labeled inside the columns as well. So the blue's labeled and the red's labeled. You could add those up and you can see the overall trend of how many students you have in all of your classes. Okay, so next up are histograms. So histograms, this is probably the classic statistical graph or chart that you're used to. It's the one that we're going to be using the most, and it's used the most overall. So histograms, they graph frequencies. So they look at your categories. I've built these off of our TVs. This is our TV data. And the classes are a little bit different because Excel was a little bit not working for me. But it's just a histogram with different classes. So it gives you the total, and notice there's no space like the bar graphs. The bar graphs all had gaps in between them. But as we know, the histograms are created from the frequency distributions specifically. And so there's no gap because we go right up until the next value and then go. And so you can label each column. You have your axes and your title. Relative frequency to histograms show relative frequencies. So this is exactly the same as the last one, except they're all relative frequencies. And I cut off the axis labels by mistake here, but this would be the relative percentage it is. So this, whatever that percentage was, whatever we calculated in the last one. So for frequency polygons, we're actually going to graph this ourselves. So frequency polygons, our x-axis is the midpoints of the classes. So our midpoints, we have 1449.5, 1549.5, 1649.5, that one's a little, 1749.5, 1849.5, and 1949.5. And we're going to extend this just slightly to do 2049.5. So you'll notice I have two values outside of our frequencies, outside of our classes. Our classes started at 1500 and went to 1999 for the TV prices. When you're doing frequency polygons, it's used for showing trends. So you want to show both the imagined class that would have been right before your first class and the imagined class that would have been right after your last class. So that's what these two data points are. And then we can, 3, 4, 1, 3, 5, 7 label, and this would be the frequency over here. And so our midpoints are actually acting as stand-ins for the whole class itself. So 1549 is the midpoint of our first class, 1500 to 1599, but it is representing the whole class itself. And so we had 2 in that class. 1649 we had 5, if I'm remembering correctly. 1749 we had 4, 1849 we had 5. Did we have 5? I can't remember. It's not really important. 1949, let's say we had 3. I can't remember. And then your first and last are always 0 and 0. And the reason this is called a frequency polygon is because then you connect the dots with nice straight lines. Mostly straight, except for that last one for me. And so this gives us a nice trend line. You can see where the bulk of the TVs are priced from 1600, the 1649 to 1849, the 1600 to 1899, those 3 classes. You can see the outliers and you can see where there are none. So again, this is just a trend in your data. It shows you the trend of, as you move through your classes, where is your frequency, where are they distributed? Are they distributed evenly or not? Obviously, these are not correct for us because I wrote down the wrong values, but not a big deal. But that's what a frequency polygon is. So next up we have the Ogives, which is a fun term. So ogives represent frequency distributions based on their cumulative frequencies. So very similar to the frequency polygon. You're going to start at 1499.5. That's a 4, not a 9. 1449.5. Again, using the midpoints, 49.5, 1649.5, 1749.5, 1849.5, and 1949.5. So the difference between ogives and frequency polygons is you start with your axes, the corner, your origin of your axes at the midpoint, the fake midpoint of the fake class right before your final class or your lowest class. And now you don't go past your highest class because we're doing cumulative frequencies. So the cumulative frequency at this class is 0. And then we would need some axes, some y-axis tick marks. So I'm going to go by 5s. And we talked about, or we will talk about scaling in a future section, and then a very next section actually. So at 1449, we don't have this class. There's no TVs priced in that range in our data. At 1549, we have 3, if I'm remembering correctly. So put a little point here. We don't need to be perfect. At 1649, the cumulative frequency jumps up to 7. At 1749, the cumulative frequency jumps up to 12. At 1849, the cumulative frequency is at 15, I believe. Or is it 17? 17. Can't remember the numbers off the top of my head. And our final one puts us at the top at 20. So, and then you create your trend. And so it's another way to represent trends in your data without using the frequency polygon on the other side here. But it's cumulative frequencies. That's the important part. So this is cumulative frequency. And this is our class midpoints. So the next type of graph is the stem and leaf plots. And these can be used to, they're just another way to organize your data. So we're going to construct a little stem and leaf plot here. So the way stem and leaf plots work is we set up a little table. And these are our stems. These are our leaves. Over here is all the leftmost digits that we see. So we see 0, 1, 2, and 3. And the leaves on the right are all the rightmost digits in our data that we see. So there are no single digit numbers here. With the 1, there's an 18, there's a 19, moving along through here, 19, then another 18, then another 18, and then two 17s, 7 and 7. Those are our leaves. And for the 2s, we have 23, 24, 27, 21, 26, 22, 27, 25, 29, 24, 20, and then 26. And for the 30s, we have 31, 32, and 35. And you always put a key with your stem and leaf plot. So the key here is 1/7. This is read as 17 in the data set. And so all this is a way to organize the data. And again, you can kind of see the distribution. Where are your most data values if you were going to put classes? So you're going to pause here, and you can finish up this section in the next video. And we're back here, section 2.2. We just finished looking at stem and leaf plots. So just to review a little bit here, the stems are all the leftmost digits, the leaves are all the rightmost digits, and you just list out all your leaves. You can break one row into two if you want. Something I didn't mention on the last one. So if you didn't like how long this was, you could put another stem of 2. You're allowed to do that. The next type of chart we have is the dot plot, and these are a lot like stem and leaf plots. They're used like stem and leaf plots to organize, but they kind of look like bar graphs. So we're not going to use any of our data because none of it works well with dot plots specifically, but essentially you have a number line, and then you have dots to tell you how many data points are there. All right, so it's a dot plot. You can read that as there's a 5, there's a 11, 12, 13, 21, 22, 23, 31, 41, no 5s, 61, 62, 63, just like that. Dot plots are really uncommon, but they're an avenue you can take. Stem and leaf plots are almost always better because you can see the data and it's easy to understand because you always include this key. I just realized I didn't write data. So the full list of charts and graphs you can find on page 85. The last one that we're going to be looking at, so this is going to be a short section. The last one is the line graphs. And so these are very special. They're all about time data, where your x-axis is always time. So here we have months of the year, and we have whatever data we are tracking each month. So you could use a line graph if you go back to our side-by-side bar graphs when we were tracking students and courses. A line graph would be another choice for that data. If you were only looking at one class, you can have 2 classes represented by another line on here. But this is almost always the go-to graph or chart when you're dealing with time. So that's the end of 2.2.